Something from beyond our solar system is heading straight toward Earth. Right now. Not in some distant, theoretical future that we can comfortably ignore, but this month. December. Scientists have been tracking it for months, and in just days, it makes its closest approach to our planet. And here's what makes your heart skip a beat. A Harvard astrophysicist recently calculated that the probability of this object's trajectory being completely natural is less than 1 in 500. Let that sink in for a moment. We're talking about something that originated from interstellar space, traveled unimaginable distances through the cosmic void, and is now passing through our cosmic neighborhood with a flight path that has some of the world's leading scientists raising their eyebrows. This isn't some clickbait headline designed to get your attention. This is 3I Atlas, and it's the third confirmed interstellar visitor ever detected by humanity. In all of recorded history, we've only confirmed 3 objects that came from beyond our solar system, and one of them is approaching Earth right now. You've probably seen scattered headlines about this. Maybe a friend shared something on social media, or you caught a brief mention on the news between stories about politics and weather. But what you haven't gotten is the full picture. What you haven't heard is why a respected scientist from one of the world's most prestigious universities is suggesting that this object's behavior doesn't quite add up, why its trajectory seems to defy the odds of random chance, why its approach to Earth specifically has triggered questions that make even seasoned astronomers uncomfortable. Stay with me here, because in the next 15 minutes, we're going to investigate this together. We're going to look at the actual data, the real science, and yes, we're going to answer the question that's probably nagging at you right now: are we in danger? But more than that, we're going to explore what this visitor from the stars reveals about our place in the universe, about the threats we face from space, and about whether we're truly prepared for what might come from the darkness between solar systems. This isn't about spreading fear. It's about understanding, because right above our heads, while most of the world goes about their daily routines completely unaware, something extraordinary is happening. An object that has traveled through interstellar space for potentially millions of years is passing by our planet. And whether it's a threat or not, whether it's natural or something else entirely, the simple fact that we're living through this moment makes it worth paying attention to. Here's what we know for certain. 3I Atlas was confirmed as an interstellar object after careful analysis of its trajectory and velocity. It's moving through our solar system at speeds that prove, without question, that it didn't originate here. The mathematics are clear on that point. It came from somewhere else, from the space between stars, from regions of the galaxy we can only imagine. It already passed its closest point to the Sun, called perihelion, back in late October, and now it's on an outbound path that will take it back into the interstellar medium. But before it leaves our solar system forever, it passes relatively close to Earth. And that's where things get interesting. The closest approach happens in mid-December. We're talking about a cosmic near miss by astronomical standards, though what close means in space is very different from what it means here on Earth. But here's the part that has scientists talking: this object isn't behaving quite like typical comets. It's showing characteristics that raise questions. Its jets of gas and dust, the way it reflects light, the precise angle of its trajectory through our solar system's planetary plane. All of these factors have caught the attention of researchers who spend their lives studying these phenomena. And then there's the Harvard connection. Professor Avi Loeb, a scientist whose credentials are impeccable, has been analyzing this object intensely. He's the former chair of Harvard's astronomy department. He's published hundreds of scientific papers. He's advised NASA and collaborated with leading researchers worldwide, and he's gone on record stating that the probability of 3I Atlas's trajectory being entirely accidental is approximately 0.2%, 0.2%. Those are lottery winning odds, except we're not talking about money. We're talking about an object from interstellar space whose path through our solar system seems almost impossibly aligned with Earth's position. Now, before you start imagining science fiction scenarios, we need to be clear about something. These claims are controversial. They're disputed by many scientists. The astronomical community is deeply divided on how to interpret these observations. Some researchers think Loeb is reading too much into the data, seeing patterns that aren't really there. Others think he's asking important questions that deserve serious investigation. But regardless of where you stand on the interpretation, the basic facts are undeniable. Something from beyond our solar system is passing by Earth this month, and it's unusual enough that serious scientists are having serious debates about what it means. So what's really happening here? Is this a natural comet following the predictable laws of physics and gravity, just like countless other objects that have passed through our solar system over billions of years? Or is there something more to this story? Are we looking at evidence of something we've never encountered before? And most importantly, the question that brought you here, are we in any danger from this cosmic visitor? You need to know this. Not because I want to scare you, but because we live in an era where, for the first time in human history, we can actually detect and track objects coming from interstellar space. We have the technology to see them approaching, to calculate their trajectories, to analyze their composition and behavior. And with that capability comes responsibility. The responsibility to understand what we're seeing, to separate fact from speculation, and to make informed judgments about cosmic risks. This matters whether you're watching from New York or New Delhi, from London or Lagos. The sky above you is the same sky, and what's moving through it right now doesn't recognize borders or nationalities. If there's a threat, it's a threat to everyone. If there's a discovery to be made, it belongs to all of humanity. This is one of those rare moments where we're all in this together, sharing the same planet, looking up at the same visitor, asking the same questions. If you want the truth about what's approaching Earth, if you want to understand what the science really says beneath the sensational headlines, hit that like button right now and drop a comment telling me where you're watching from and whether you're feeling more concerned or more curious about 3i Atlas. Let me know, because we're about to dive deep into this investigation together, and I want to know who's here with me, paying attention to what's happening above us while the rest of the world scrolls past. Let's get into this. Let's establish a foundation here, because before we can explore the controversies and the questions, we need to understand exactly what 3i Atlas is according to the confirmed, peer-reviewed science. No speculation yet, just the facts that astronomers agree on. 3i Atlas is an interstellar comet. That designation, 3i, tells you something important right away. It's the third interstellar object ever confirmed by humanity. The first was Oumuamua, discovered in 2017, which sparked enormous debate and continues to puzzle scientists. The second was Borisov, found in 2019, which behaved more like a typical comet and gave researchers their first real opportunity to study interstellar material in detail. Now we have 3i Atlas, and it's adding another chapter to our very short history of detecting visitors from beyond our solar system. What makes something interstellar isn't just where it came from, but how it's moving. Every object in our solar system orbits the sun in predictable paths, bound by gravity. Planets, asteroids, comets, they're all held in the sun's gravitational embrace, traveling in elliptical orbits that bring them around again and again. But interstellar objects are different. They're moving so fast that the sun's gravity can't capture them. They come in on hyperbolic trajectories, meaning they pass through our solar system once and then leave forever. The mathematics of their motion proves they originated elsewhere, perhaps orbiting a distant star billions of miles away, until something knocked them loose and sent them wandering through the galaxy. 3i Atlas entered our solar system from interstellar space, passed relatively close to the sun earlier this year, and is now on its way back out. It's moving at extraordinary speed, fast enough that our sun's immense gravitational pull can only bend its path slightly before it escapes into the cosmic ocean again. Think about that for a moment. The sun is so massive that it holds 8 planets, countless asteroids, and trillions of comets in its gravitational grip across billions of miles. But 3i Atlas is moving so fast that it's just passing through, unable to be captured, destined to leave our solar system and journey back into interstellar space. The size of this object is estimated to be larger than the previous 2 interstellar visitors, though the exact size remains uncertain. Early estimates suggested it could be as large as 10 kilometers in diameter, but more recent observations from the Hubble Space Telescope in August 2025 have refined these estimates significantly. Current data indicates the nucleus is likely between 0.5 and 5.6 kilometers in diameter, roughly between 0.3 and 3.5 miles across. This uncertainty exists because the nucleus is surrounded by a reflective dust coma that makes it appear larger and brighter than it actually is. Even with this uncertainty, 3i Atlas appears to be substantially larger than Oumuamua and comparable to or larger than Borisov. It's large enough to be tracked and analyzed in detail as it moves through space. It's composed of ice, rock, and dust, the frozen remnants from some distant stellar system. material that has been drifting through the galaxy for potentially millions or even billions of years before passing through our neighborhood. Right now, as you're watching this, 3i Atlas has already completed its swing around the Sun and is heading outward. It's currently positioned beyond Earth's orbit, moving away from our star. But here's what matters for our investigation: its trajectory brings it to its closest point to Earth on December 19th. That closest approach happens at a distance of approximately 1.8 astronomical units, about 170 million miles or 270 million kilometers from our planet. In everyday terms, that's nearly twice the distance between Earth and the Sun. It's far beyond the Moon, far beyond any satellites we've launched, in a region of space that poses absolutely no threat to our planet. In astronomical terms, it's a reasonably close pass. In human terms, it's unimaginably distant. But distance isn't the only thing that matters here. What has scientists watching carefully is the object's behavior as it moves through space. Like many comets, 3i Atlas is active. It's releasing gas and dust as solar radiation heats its surface, creating a tail and a surrounding cloud of material called a coma. This is normal comet behavior, something we've observed thousands of times with comets native to our solar system. But what's unusual is the specific pattern of that activity, the direction of the jets of material being released, and the way this particular comet is reflecting light back to our telescopes. And then there's the trajectory itself. 3i Atlas is traveling through the plane where most of the solar system's planets orbit. That plane, called the ecliptic, is where you'd find Mercury, Venus, Earth, Mars, and the other planets all orbiting roughly along the same flat disk around the Sun. Most objects that enter our solar system from interstellar space could come from any direction. Above the plane, below it, or at steep angles to it. The universe is three-dimensional, after all, and there's no reason for an interstellar traveler to align itself with our particular solar system's layout. But 3i Atlas is moving almost exactly along this planetary plane, and that alignment is part of what has caught some scientists' attention. The speed at which it's moving is also noteworthy. Interstellar objects travel fast, but there's a range of velocities they could have depending on where they came from and how they were ejected from their home systems. 3i Atlas is moving fast enough to confirm its interstellar origin beyond any doubt, but the specific velocity and direction raise questions about its history. Where did it come from? What star system might have been its home? What event sent it on this journey through the galaxy? These are questions that may never be fully answered, but they're part of what makes this object scientifically valuable. What we can say with absolute certainty is that 3i Atlas is real. It's being tracked by multiple observatories around the world and in space, and its trajectory has been calculated with high precision. Agencies like NASA and the European Space Agency have confirmed its path. There's no ambiguity about where it's going or when it will reach certain positions relative to Earth. The orbital mechanics are well understood, and the predictions are reliable. This isn't a matter of guesswork or rough estimates. When scientists say it will reach its closest point to Earth on a specific date in December, that's based on solid mathematical modeling backed by repeated observations. So we're dealing with a confirmed interstellar comet, the third ever detected, moving through our solar system on a path that will bring it to its nearest point to Earth this month, before it continues its journey back into the space between stars. It's being monitored, studied, and analyzed by professional astronomers using some of the most sophisticated instruments humanity has ever built. That's the baseline. That's what we know for certain. But here's where things start to get complicated. Knowing what something is doesn't always explain why it's behaving the way it is. And it's in those unexplained behaviors, those slight anomalies and unusual characteristics, that questions begin to emerge. Questions that have led one very prominent scientist to make claims that have divided the astronomical community and captured public attention. So if this is just another comet, even if it's from interstellar space, why is a Harvard professor suggesting that its trajectory has less than a 1% chance of being completely natural? What did he see in the data that made him go public with such a controversial statement? That's what we need to investigate next, because that's where the real mystery of 3i Atlas begins. Professor Avi Loeb is not someone who makes claims lightly. This is a man who has spent decades at the pinnacle of academic astronomy, former chair of Harvard's astronomy department, author of hundreds of peer-reviewed papers, a scientist who has collaborated with Nobel Prize winners and advised NASA on critical projects. When someone with that kind of credibility speaks, people listen, even when what he's saying makes them uncomfortable. And what Loeb has been saying about 3I Atlas makes a lot of people very uncomfortable. In recent statements and calculations, Loeb has put forward an analysis that challenges the assumption that 3I Atlas is simply a natural comet, following the random paths that physics and gravity would predict. He's calculated that the probability of this object's specific trajectory, its path through our solar system, its alignment with the planetary plane, its approach distance to Earth, being entirely accidental is approximately 0.2%, 0.2%. To put that another way, according to his analysis, there's a 99.8% probability that something other than random chance is influencing this object's path. Now, before we go further, we need to be absolutely clear about what Loeb is and isn't saying. He's not claiming with certainty that 3I Atlas is artificial. He's not saying definitively that it's some kind of probe or spacecraft or alien technology. What he's saying is that the statistical probability of its trajectory being purely natural is extremely low, and that this fact deserves serious scientific investigation rather than immediate dismissal. He's calling for an open-minded approach to analyzing the data, for considering possibilities that might seem unlikely but can't be ruled out without evidence. So what specifically about 3I Atlas's trajectory has led Loeb to these conclusions? There are several factors that, when combined, create a pattern that he finds statistically improbable. First, there's the planetary plane alignment we mentioned earlier. The solar system's planets all orbit the sun along roughly the same flat plane. If you could look at our solar system from the side, you'd see the planets strung out along a relatively thin disk. Most comets native to our solar system also travel in or near this plane because they formed from the same primordial disk of material that created the planets. But 3I Atlas came from outside our solar system. It originated in interstellar space, where there's no particular reason for it to be aligned with our planetary plane at all. The galaxy is three-dimensional. An object approaching from interstellar space could come from literally any direction, from above the plane, from below it, or at any angle in between. Yet 3I Atlas happens to be traveling almost exactly along this planetary plane. According to Loeb's analysis, if you randomly selected a trajectory for an interstellar object entering our solar system, the odds of it being this closely aligned with the planetary plane by pure chance are very low. It's not impossible, but it's statistically unlikely. And when something unlikely happens, scientists pay attention. Second, there's the specific distance at which 3I Atlas is passing by Earth. It's not coming extremely close. We'll get to the actual safety issue later, but it's coming close enough to be noteworthy. Out of all the possible paths an interstellar object could take through our solar system, this one happens to bring it to a relatively close approach to our planet specifically. Again, not impossible by any means, but when you start combining unlikely factors, the compound probability starts to become more interesting. Third, and perhaps most intriguing to Loeb, is the behavior of the object's outgassing and jets. When comets get close to the sun, they heat up, and frozen materials on their surface begin to vaporize and escape into space. This creates jets of gas and dust that can actually push on the comet slightly, changing its trajectory in small but measurable ways. This is called non-gravitational acceleration, forces acting on the comet beyond just gravity. It's completely normal and observed in many comets. What's unusual about 3I Atlas, according to some observations, is the direction and timing of these jets. Multiple research teams have noted that the object's outgassing behavior doesn't follow exactly the pattern you'd expect from a typical comet. The jets seem to be oriented in ways that are difficult to explain with simple models of how comet surfaces respond to solar heating. Some observations suggest the jets are directed in a manner that seems more organized than random. And here's where Loeb's analysis becomes most controversial. He suggests that the pattern of jet activity could be consistent with something other than purely natural processes. Now we need to talk about what Loeb has called the space entrepreneur hypothesis. This is where his analysis ventures into territory that makes many of his colleagues deeply skeptical. Loeb has suggested, not as a proven fact but as a possibility worth investigating, that 3I Atlas's unusual characteristics could be consistent with artificial intervention. He's proposed that an advanced civilization might use comets or comet-like objects as vessels for exploration or transportation, taking advantage of natural icy bodies as both raw material and camouflage. In this hypothesis, what appears to be a comet might actually be a comet being used for some purpose, with its trajectory and behavior influenced by technology rather than being solely at the mercy of gravity and solar heating. This is, to put it mildly, a controversial idea. The vast majority of astronomers reject it as unnecessary speculation, unsupported by compelling evidence. They argue that while 3I Atlas may have some unusual characteristics, those characteristics can be explained by natural processes we already understand, or by slight variations in comet composition and structure that we haven't fully catalogued yet. They point out that Loeb has a history of making sensational claims about potential extraterrestrial technology, particularly regarding Oumuamua, the first detected interstellar object, which he has long suggested might be an alien artifact. Critics say he's pattern matching, seeing intentional design where there's only natural variation. And this criticism isn't without merit. Science requires extraordinary evidence for extraordinary claims, and suggesting that an interstellar object might be artificial or influenced by technology is about as extraordinary as claims get. The burden of proof for such an assertion is enormous, and as of now, that level of proof simply doesn't exist. There are natural explanations available for every unusual characteristic 3I Atlas displays, even if some of those explanations require assumptions about comet composition or structure that we can't verify directly without a close-up mission. But here's where it gets interesting. Loeb isn't asking people to accept his hypothesis as fact. He's asking for it to be investigated seriously rather than dismissed out of hand. He's arguing that the scientific method requires us to consider all possibilities that aren't ruled out by evidence, even unlikely ones, and to design observations and tests that could potentially distinguish between natural and artificial explanations. He's saying that in an age where we know for certain that billions of Earth-like planets exist in our galaxy, where the ingredients for life are common throughout the universe, it's not scientifically unreasonable to consider that objects passing through our solar system might occasionally be more than just rocks and ice. Most of the astronomical community disagrees with this approach, at least regarding 3I Atlas. They see it as an interesting comet with some unusual features, but nothing that requires invoking exotic explanations. They worry that too much attention on unlikely scenarios distracts from the actual scientific work of understanding interstellar objects and their natural properties. They're concerned that sensational speculation damages public trust in science and feeds conspiracy theories. This tension between Loeb's perspective and the mainstream scientific view is important to understand because it frames everything else about how we interpret 3I Atlas. Are we looking at a garden-variety interstellar comet that happens to have some interesting quirks? Or are we looking at something that demands a deeper investigation because the statistics don't quite add up? The answer to that question depends partly on the data and partly on how you approach the philosophy of scientific inquiry, whether you lean toward conservative explanations that stick with what we already know, or whether you lean toward investigating outliers more aggressively on the chance that one of them might reveal something genuinely new. What we can say for certain is this: Ivy Loeb's claims about 3I Atlas remain highly debated and unproven within the broader astronomical community. His 0.2% probability calculation is based on his own analysis and assumptions, which other scientists have questioned. His suggestions about artificial influence or the space entrepreneur hypothesis are considered speculative by the vast majority of his peers. These ideas do not represent scientific consensus, and they should be understood as one scientist's controversial interpretation of data that most others interpret very differently. But whether you agree with Loeb or not, his prominence and his willingness to ask uncomfortable questions have put 3I Atlas in the spotlight. They've forced the scientific community to look more carefully at this object, to gather more data, to refine their models and explanations, and they've certainly captured public attention, which brings us back to the question that probably brought you here in the first place. With all this controversy, with all these unusual characteristics, with a respected Harvard scientist raising alarms about statistical improbabilities and potential artificial influence, we need to answer the fundamental question directly. Is 3I Atlas actually a threat to Earth? Should we be concerned, or can we breathe easy? Let's get to the answer. Here's the answer you came for, delivered straight and backed by every authoritative source that matters. No. We are not in danger from 3I Atlas, not even close. The object poses absolutely zero threat to Earth, and that's not a guess or a hopeful assessment. It's a mathematical certainty confirmed by multiple space agencies, using the most precise orbital tracking technology available. Let's break down exactly why you can sleep soundly despite all the dramatic headlines and controversial scientific debates. The distance at which 3i Atlas is passing Earth is vast. When astronomers say close approach, they're using astronomical language, and what counts as close in space bears no resemblance to what close means in everyday life. This object is passing Earth at a distance that is many times greater than the distance between Earth and the Sun. To put that in perspective, light from the Sun takes about 8 minutes to reach Earth. 3i Atlas at its closest point will be multiple times that distance away from us. It's so far away that if you could somehow stand on its surface and look back at Earth, our planet would be nothing more than a tiny dot of light indistinguishable from the stars around it. NASA has confirmed this trajectory. The European Space Agency has confirmed it. Ground-based observatories around the world have tracked this object repeatedly and calculated its path with extraordinary precision. The mathematical models that predict orbital mechanics are among the most reliable tools in all of science. When astronomers say they know where 3i Atlas is going, they're not guessing. They're using the same physics that allows us to send spacecraft to distant planets with pinpoint accuracy, the same calculations that predict eclipses centuries in advance. The margin of error in these predictions is microscopic compared to the actual distances involved. And here's something that should give you even more confidence: we now have unprecedented confirmation of 3i Atlas's trajectory, thanks to a breakthrough in observational technique. The European Space Agency's JOIC mission, a spacecraft currently on its way to explore Jupiter's moons, made history by becoming the first planetary spacecraft ever used to triangulate the position of a comet through parallax measurement. In simpler terms, by combining observations from JIC in its current position with observations from Earth-based telescopes, scientists were able to measure 3i Atlas's position and trajectory with greater precision than ever before. This wasn't just another observation. This was a new level of certainty about exactly where this object is and where it's going. The trajectory has been confirmed. No deviations have been detected. The object is following exactly the path that physics predicts it should follow, moving under the influence of the Sun's gravity and the small pushes from its own outgassing, with no surprises and no unexpected changes. It passed the Sun, it's now moving outward, and its path carries it safely past Earth before it continues into interstellar space. There's no possibility of impact, no chance of a closer approach than predicted, no scenario where this object suddenly changes course and becomes a threat. So why do the headlines sound so alarming? Why does close approach trigger anxiety when the reality is completely safe? This is partly about how astronomical news gets translated into public communication. When a scientific paper describes an interstellar object making its closest approach to Earth, that's technical language describing a noteworthy event for observation purposes. It means this is the best opportunity to study the object when it's at its nearest point, and therefore brightest and easiest to observe in detail. It doesn't mean the object is threateningly close in any practical sense. But when that language gets filtered through news media, through social media, through the natural human tendency to focus on potential threats, it transforms. Interstellar visitor makes close approach to Earth, becomes object from beyond solar system heading toward Earth, becomes are we in danger from cosmic visitor. Each step in that translation adds a layer of alarm that wasn't present in the original scientific statement, and suddenly something that astronomers see as an exciting research opportunity becomes something that sounds like it might require emergency preparations. Add in a prominent scientist making controversial claims about unlikely trajectories and potential artificial origins, and you've got a perfect storm of public concern. But here's what's crucial to understand: the controversy about whether 3i Atlas has unusual characteristics has absolutely nothing to do with whether it's dangerous. Loeb's claims about statistical improbability and potential artificial influence, even if they were completely correct, wouldn't change the fact that the object's trajectory is precisely known and poses no threat. You could hypothetically have an artificial probe from an advanced civilization passing through our solar system, and it still wouldn't be dangerous as long as its trajectory keeps it at a safe distance, which in this case, it absolutely does. The safety assessment and the mystery assessment are separate questions. Is 3i Atlas safe? Yes, completely. Is 3i Atlas behaving in ways that raise interesting scientific questions? That's a different question entirely, and one we'll keep exploring. But they don't depend on each other. An object can be perfectly safe and still scientifically fascinating. A comet can pose zero threat to Earth and still have unusual characteristics worth investigating. This is actually a perfect example of how modern astronomy works at its best. We have the capability to detect objects like this early, to track them precisely, to calculate their trajectories with certainty, and to provide the public with accurate information about any potential risks. The system worked exactly as it should. 3I Atlas was detected well before it posed any kind of concern. Its trajectory was calculated and confirmed through multiple independent observations. The scientific community assessed the threat level, which is 0, and communicated that to the public. No alarms, no emergency preparations, no need for concern. Compare that to how things would have gone a century ago. An object like this would have been completely undetectable until it was already passing by. If we noticed it at all, we would have had no way to track it, no ability to predict its path, no means of assessing whether it posed a threat. We would have been blind to cosmic events happening right above our heads. But today we're not blind. We have eyes on the sky. We have the mathematics to understand what we're seeing. We have the communication systems to share that knowledge globally. And in this case, we have the confidence to say with certainty, this object is not a threat. The fact that you're hearing about 3I Atlas at all is a testament to how much our capabilities have advanced. A few decades ago, this would have been a completely unknown event, something happening in the darkness of space without any human awareness. Now it's being tracked by multiple telescopes, analyzed by research teams around the world, and discussed by millions of people who have access to real information about what's happening above them. That's progress. That's the scientific civilization we've built. So to the question in the title of this video, are we in danger? The answer is a definitive no. 3I Atlas will make its closest approach to Earth in mid-December. It will pass at a completely safe distance, and it will continue on its journey back into interstellar space without affecting our planet in any way whatsoever. You don't need to prepare. You don't need to worry. You don't need to lose sleep over this cosmic visitor. But, and this is important, just because we're not in danger doesn't mean there's nothing interesting happening here. The absence of threat doesn't equal the absence of significance. In fact, now that we've established that we can watch this event with curiosity rather than fear, we can start asking the more interesting questions. What makes this object so unusual that it's generating scientific controversy? Why are some of its characteristics puzzling researchers? What can we learn from having an interstellar visitor pass through our cosmic neighborhood? Those questions don't carry the weight of survival, but they carry something equally valuable: the opportunity to understand our universe a little bit better. And that's what we're going to explore next, because the safety question is settled. But the mystery of 3I Atlas is just beginning. Now that we've established you're not in danger, we can do something more valuable than worrying. We can appreciate just how remarkable this object actually is. Because even if 3I Atlas poses no threat, even if the most exotic explanations for its behavior turn out to be wrong, the simple fact that we're observing an interstellar visitor passing through our solar system is extraordinary, and the specific characteristics this visitor is showing make it even more fascinating than a simple cosmic passerby would be. Let's start with the fundamental rarity here. We've confirmed exactly 3 interstellar objects in all of human history. 3. For the entire span of our species' existence, we've been completely blind to these visitors. They've passed through our solar system countless times over millions of years, and we never knew they were there. It wasn't until 2017 that we detected the first one, Oumuamua, and that detection only happened because our astronomical survey systems had finally reached a level of sensitivity and coverage that could catch these fast-moving objects as they passed through. Before that, they were invisible to us, ghosts moving through the darkness without leaving a trace we could perceive. The second interstellar object, Borisov, arrived in 2019. That one behaved much more like traditional comets we're familiar with from our own solar system, which actually made it incredibly valuable for scientific study. It gave researchers their first opportunity to analyze material from another stellar system, to compare its composition to comets native to our own neighborhood, to see whether the building blocks of solar systems are consistent across the galaxy, or whether different stellar environments produce different types of frozen bodies. Now we have 3I Atlas, the third confirmed interstellar visitor, and it's proving to be neither as mysterious as Oumuamua nor as straightforward as Borisov. It's somewhere in between, showing characteristics of typical comet behavior while also displaying features that don't quite fit the standard models. And that's exactly the kind of object that tends to teach us the most. because it's in the edge cases, in the objects that don't fit cleanly into our existing categories, that we discover the limits of our current understanding. So what exactly makes 3I Atlas unusual? Let's go through the key characteristics that have scientists paying such close attention. First, there's the composition puzzle. All comets are made primarily of ice, rock, and dust, frozen volatiles that were incorporated into these objects during the formation of their home solar systems. But the specific mix of materials, the ratios of different ices, the types of rock and mineral content, these can vary depending on where and how a comet formed. When 3I Atlas is heated by the sun and releases gas, that gas can be analyzed spectroscopically. We can literally look at the light passing through the gas cloud and identify what molecules are present based on which wavelengths are absorbed or emitted. This gives us a chemical fingerprint of the comet's composition. What researchers have found is that 3I Atlas's composition shows some unexpected features. The ratios of certain molecules don't quite match what's typical for comets from our solar system, which isn't surprising given that it formed around a different star, but they also don't match Borisov, the other interstellar comet we've studied in detail. Every interstellar visitor gives us a new data point about what exists out there in the galaxy, and so far, we don't have enough data points to know what's normal and what's unusual for these objects. Each one is expanding our understanding of the range of possibilities. Then there's the brightness pattern. As comets approach the sun, they typically brighten in predictable ways as their surfaces heat up and more material begins to vaporize. As they move away from the sun, they dim as they cool down and activity decreases. 3I Atlas has shown brightness variations that don't follow this simple pattern exactly. There have been unexpected increases in brightness at times when the activity should have been decreasing, and periods where the object appeared dimmer than models predicted. These variations could be explained by the comet's rotation. As it spins, different areas of its surface face the sun, and if the surface has regions with different compositions or different amounts of volatile ices, you'd see brightness changes as those regions rotate in and out of sunlight. But the specific pattern of brightness changes observed with 3I Atlas has puzzled some researchers. The variations seem more complex than simple rotation would easily explain. There might be active regions on the surface that turn on and off, or the rotation might be more complicated than a simple spin, or the object's shape might be irregular in ways that affect how much sunlight it reflects at different orientations. All of these are natural explanations, but they require making assumptions about the object's physical properties that we can't verify directly without sending a spacecraft there. The jet behavior is perhaps the most discussed unusual characteristic. When comet surfaces heat up, gas escapes through vents or cracks, creating jets that shoot out into space. These jets carry dust with them, creating the visible tails that make comets so spectacular. The direction and strength of these jets depend on where the active regions are on the comet's surface and how the object is oriented relative to the sun. For most comets, the jet activity follows fairly predictable patterns based on solar heating. The parts of the surface facing the sun become active, the parts in shadow are quiet. Multiple observation teams have noted that 3I Atlas's jets don't seem to follow this pattern as cleanly as expected. The jets appear to have directional preferences that are difficult to explain purely through solar heating models. Some observations suggest the jets are more organized, more directed, than the somewhat random distribution you might expect from a natural surface with irregular composition. This is where A.V. Loeb's analysis focuses heavily. He argues that this organized jet behavior is statistically unusual and could indicate something other than purely natural outgassing. Most astronomers who have looked at the same data disagree with this interpretation. They argue that comets are complex objects with irregular shapes, heterogeneous surfaces, and rotation states that can be quite complicated. All of these factors can produce jet patterns that look organized without requiring any exotic explanations. The apparent organization might just be a consequence of the comet's specific shape and how its rotation interacts with solar heating. We've seen comets from our own solar system show surprising jet behavior too, and in every case where we've been able to study them closely, natural explanations have proven sufficient. But the debate itself is valuable because it's pushing researchers to look more carefully at the data, to develop better models of how comets behave, to think more rigorously about what constitutes normal versus unusual behavior. Science advances not just through consensus, but through the productive tension between different interpretations of the same observations. And then there's that planetary plane alignment we keep coming back to. The fact that 3i Atlas is traveling so close to the plane where our solar system's planet's orbit is striking, because there's no particular reason it should be. The galaxy is three-dimensional. Interstellar objects could arrive from any direction. The fact that this one happens to be aligned with our planetary plane could be pure coincidence. After all, unlikely things happen all the time if you observe enough events. But it's the kind of coincidence that makes you look twice, that makes you wonder whether there's more to the story. Some scientists have suggested that there might actually be natural reasons why interstellar objects would show some preference for traveling along galactic planes rather than being completely randomly distributed in direction. The galaxy itself has structure. There's a galactic disk where most stars orbit, and the dynamics of how objects get ejected from stellar systems might have some bias towards certain directions related to that galactic structure. If that's true, then finding interstellar visitors aligned with planetary planes might be less surprising than pure random chance would suggest. But this is cutting-edge research where we simply don't have enough data yet to know for sure. What we can say is that every one of these unusual characteristics, the composition variations, the brightness fluctuations, the jet directionality, the trajectory alignment, has potential natural explanations. None of them require invoking anything beyond known physics and known types of celestial objects. But taken together, they create a profile that's interesting enough to justify intense scientific attention during the December observation window. This is our chance to gather as much data as possible while 3i Atlas is at its closest and brightest to try to resolve some of these mysteries and better understand what we're looking at. And that's actually the most important thing about 3i Atlas from a scientific perspective. It's an opportunity to study interstellar material up close, to analyze the composition of matter from another stellar system, to test our models of comet behavior under unusual circumstances, to learn how to better detect and characterize these visitors so that when the next one comes, and there will be a next one, we're even better prepared to study it. We're living through one of the first times humanity has been able to observe and analyze objects from beyond our solar system. That's historically significant regardless of whether these objects turn out to be exotic or mundane. We're expanding our reach, extending our scientific capabilities into territory we couldn't access before. Every interstellar visitor is a messenger carrying information about regions of space we may never be able to visit in person. They're bringing the galaxy to us, delivering samples from stellar systems light years away, giving us glimpses of environments and processes that exist far beyond our direct reach. So yes, 3i Atlas is unusual. It's showing us things we didn't expect, raising questions we haven't fully answered, challenging our models and our assumptions. But that's exactly what makes it valuable. If it were just another ordinary comet, it would be less interesting scientifically, even though it's coming from interstellar space. The fact that it's puzzling, that it's generating debate, that it's making scientists think harder about what they're seeing, that's what makes it a significant event worth paying attention to. But understanding why scientists are so focused on this object requires us to zoom out and look at the bigger picture of why interstellar visitors matter at all, and what we're trying to learn from them. That's the context we need to really appreciate what's happening here. Let's shift gears here and talk about something that 3i Atlas isn't going to do, but that's worth understanding anyway. We've established that this particular object poses no threat to Earth. But the reason we track these objects so carefully, the reason agencies like NASA maintain programs dedicated to detecting and monitoring near-Earth objects, is because cosmic impacts are real. They've happened throughout history, and they remain one of the few truly existential threats humanity faces that we can actually do something about. So let's explore the what-if scenario, not about 3i Atlas specifically, but about what would actually happen if an object like this, or any comet or asteroid, were on a collision course with Earth. This isn't fear-mongering. This is education about a risk that's real, quantifiable, and worth understanding even though it's extremely unlikely in any given time frame. First, let's talk about probability. The chances of a civilization-threatening impact happening in your lifetime are incredibly small. We're talking about events that occur on timescales of tens of thousands to millions of years. Small impacts that might destroy a city happen more frequently, perhaps every few centuries. But impacts large enough to cause global catastrophe, the kind that could end human civilization, are genuinely rare. However, rare doesn't mean impossible. It means we're dealing with a low probability, high consequence risk. The kind of risk that's worth paying attention to specifically, because if it does happen, the consequences are so severe. The dinosaurs learned this lesson 66 million years ago when an asteroid struck Earth and triggered a mass extinction event. That wasn't mythology or speculation. We have the physical evidence, a layer of iridium, enriched material in rock formations around the world dating to exactly that time, chemical signatures consistent with asteroid composition, and the massive crater structure buried under Mexico's Yucatan Peninsula where the impact occurred. An object larger than a mountain slammed into Earth at cosmic velocities, released energy equivalent to billions of nuclear weapons, and changed the planet's climate so dramatically that 75% of all species went extinct. Could something like that happen again? Yes. Will it happen in our lifetimes? Almost certainly not. But the key word there is almost. We can't reduce the probability to zero, which is why we track potentially hazardous objects and why understanding impact science matters. So what determines how dangerous an impact would be? Two main factors: size and speed. Size matters because it determines how much mass is involved and therefore how much energy can be released in the collision. A small meteoroid might burn up completely in the atmosphere, creating a bright fireball but never reaching the ground. A larger object might survive atmospheric entry and create a crater, devastating the immediate impact area but not causing global effects. An even larger object could trigger regional destruction and potentially affect climate on a continental scale. And a truly massive object, something comparable to what killed the dinosaurs, could cause global catastrophe. The threshold for different levels of impact effects isn't a simple line, but roughly speaking, objects smaller than a certain size pose primarily local threats. They could destroy a city if they hit in the wrong place, but they wouldn't threaten human civilization as a whole. Objects above that threshold start to pose regional to global threats, depending on exactly how large they are and where they strike. Speed matters because impact energy scales with velocity. A comet or asteroid hitting Earth isn't like dropping a rock. It's more like a cosmic bullet moving at speeds that are almost incomprehensible in everyday terms. When something moving that fast hits the ground or ocean, it doesn't just make a hole. The kinetic energy converts almost instantaneously into heat, shock waves, and explosive force. The object and the material it strikes both vaporize in microseconds. The energy released creates a blast wave that radiates outward, capable of flattening everything for vast distances. If the impact is in an ocean, it generates tsunamis that can travel across entire ocean basins and devastate coastlines thousands of miles away. And here's what makes interstellar objects particularly interesting from a planetary defense perspective: they're fast. Objects native to our solar system that might pose Earth impact risks are already orbiting the Sun, and their relative velocities compared to Earth are bounded by the physics of solar system orbits. But interstellar objects are coming in from outside with velocities that can be significantly higher. That extra speed means more energy on impact. A smaller interstellar object could potentially do as much damage as a larger solar system object because of its higher velocity. But speed cuts both ways. Higher velocity also means less time for gravitational interactions to change the trajectory. An object moving through our solar system on a hyperbolic trajectory, like 3I Atlas, is here and gone quickly. It's not orbiting, not staying around where repeated gravitational interactions with planets could slowly alter its path over time. It shoots through, and if it's not on a collision course when it enters the solar system, it's extremely unlikely to end up on one. This is actually one of the reasons 3I Atlas was never considered a threat even before precise trajectory calculations were completed. Objects on hyperbolic trajectories have paths that are largely determined by their initial velocity and direction. Unless they happen to be aimed almost directly at Earth from the start, they're not going to hit us. The gravity of the Sun and planets can bend their paths slightly, but not enough to turn a clear miss into a collision. Now let's talk about the actual consequences if an impact did occur, because understanding the mechanism of destruction helps clarify why these events are taken seriously by scientists and governments. The immediate impact zone would experience devastation beyond anything humans have created with weapons. The energy release would be measured in terms of millions or billions of tons of TNT equivalent, depending on the object's size. Everything within a certain radius would be vaporized, simply ceasing to exist as anything but plasma and expanding vapor. Beyond that immediate zone, the blast wave would destroy structures, the thermal radiation would ignite fires across vast areas, and the seismic shock would trigger earthquakes. But for truly large impacts, the immediate destruction at the impact site isn't the main threat to global civilization. The main threat comes from what happens to the atmosphere and climate afterward. An impact powerful enough throws enormous amounts of material into the upper atmosphere. Vaporized rock, dust, debris from the destroyed asteroid or comet, all lofted high enough that it spreads globally on atmospheric currents. This material blocks sunlight, dropping temperatures worldwide. The term, impact winter, describes the climate disruption that would follow months or years of reduced sunlight, cooling temperatures, disrupted weather patterns, and devastated agriculture. For an impact in the ocean, there's also the immediate threat of tsunamis. An asteroid striking deep water would displace enormous volumes of ocean, creating waves that would radiate outward at jet aircraft speeds. By the time these waves reached distant coastlines, they'd be unimaginably destructive, washing inland for miles and wiping out coastal cities with little warning. The majority of Earth's population lives in coastal areas, which makes ocean impacts particularly threatening from a human casualty perspective. Historical precedent tells us these events happen. The dinosaur extinction is the most famous example, but it's not the only one. Geological records show multiple impact events throughout Earth's history, and we can see the scars, impact craters of various sizes and ages dotting the planet's surface, many eroded or buried but still detectable through geological surveys. Meteor Crater in Arizona is a relatively recent and well-preserved example, created by an object that was relatively small by cosmic standards, but still released more energy than a large nuclear weapon. More recently, in 1908, an explosion in Tunguska, Siberia flattened forests across hundreds of square miles. The leading theory is that this was caused by a relatively small asteroid, or comet fragment, that exploded in the atmosphere before reaching the ground. If that event had occurred over a populated area, instead of remote wilderness, the death toll would have been catastrophic, and we've observed impacts happening elsewhere in the solar system. In 1994, Comet Shoemaker, Levy 9 broke apart and slammed into Jupiter in a series of collisions that were visible from Earth. The impact scars on Jupiter's cloud tops were larger than Earth itself. That event served as a vivid reminder that these collisions still occur in the modern solar system, that the process that shaped planets billions of years ago hasn't completely stopped. So why aren't we more worried? Why isn't this a source of constant anxiety for humanity? Several reasons. First, as mentioned, the probability of a civilization-threatening impact in any human lifetime is extremely low. We're talking about playing cosmic roulette, where the odds are heavily in our favor for any given century. Second, we're now actively doing something about it. Unlike every generation of humans before us, we have the capability to detect these threats in advance and potentially do something to prevent them. NASA and other space agencies maintain surveys that scan the sky looking for near-Earth objects. They've catalogued the vast majority of the really large asteroids that could pose extinction-level threats, and none of them are on collision courses with Earth for the foreseeable future. That's not complacency. It's based on actual observations and trajectory calculations. The objects that could kill billions of people are large enough that we can see them from far away, and we've found them, and we've checked their orbits, and we're safe from them for at least the next century. The gap in our knowledge is smaller objects, things large enough to destroy a city, but small enough to be harder to detect in advance. These are still being catalogued, and there are probably many we haven't found yet. But even here, the probability of impact remains low for any specific time period. The solar system is vast, and Earth is a small target. There's also genuine progress being made on deflection technology. NASA's DART mission successfully demonstrated that we can change an asteroid's trajectory by hitting it with a spacecraft. That was a proof of concept, showing that with enough warning time, we have the potential to nudge a threatening object off course. We're not helpless. We're building the tools and knowledge to protect ourselves. And this brings us back to why objects like 3I Atlas matter in this context. Every unusual object that passes through our solar system teaches us something about the range of things that exist out there. Every object we track successfully demonstrates and improves our detection and monitoring capabilities. Every debate about trajectories and characteristics sharpens our scientific tools and our ability to assess threats accurately. We're learning, improving, building a civilization-level capability to detect and potentially prevent cosmic impacts. 3I Atlas isn't dangerous, but it's part of the larger story of humanity becoming aware of its cosmic environment and learning to navigate the risks that come with being a species living on a planet in a solar system that occasionally receives visitors from the void. That awareness, that capability, that's the real significance here. We're transitioning from a species that was blind to these threats to a species that can see them coming and might be able to do something about them. That's a remarkable achievement, and it's worth understanding and appreciating as we watch 3i Atlas pass safely by. December represents a unique window, a brief period when 3i Atlas is close enough, bright enough, and positioned well enough for some of the most powerful observation tools humanity has ever built to gather data that could answer the questions we've been discussing. This isn't just casual stargazing. This is a coordinated international effort involving space telescopes, ground-based observatories, and even spacecraft that are traveling through the solar system on other missions, but happen to be positioned where they can contribute unique perspectives. The Hubble Space Telescope, one of astronomy's most iconic instruments, has been tasked with observing 3i Atlas during its close approach. Hubble's capabilities for detailed imaging and spectroscopic analysis make it ideal for studying comets. The telescope can capture high-resolution images showing the structure of the comet's coma and tail, tracking how those features change over time as the object rotates and as solar heating varies. More importantly, Hubble can break down the light from the comet into its component wavelengths, revealing which molecules are present in the gas being released. This spectroscopic data is like a chemical fingerprint, telling us what the comet is made of and how that composition compares to comets native to our solar system. What scientists hope to learn from Hubble's observations includes better constraints on the comet's size and shape, more detailed composition analysis that could reveal unusual or unexpected molecules, and tracking of how the comet's activity changes as it moves away from the Sun. Any significant deviations from expected behavior would be caught by Hubble's precise measurements. Then there's the breakthrough observation technique that was demonstrated recently. Using the JY spacecraft to provide a parallax measurement, JYC is a European Space Agency mission currently on its way to Jupiter, where it will study the planet's icy moons. But right now, JYC is positioned at a location in space that's significantly distant from Earth, and that separation turned out to be scientifically valuable for observing 3i Atlas. By observing the comet simultaneously from JYC's position and from Earth-based telescopes, astronomers could measure the slight difference in the comet's apparent position against the background stars. This parallax effect is the same principle your brain uses to perceive depth. Seeing something from two different positions allows you to triangulate its exact location. This was the first time a planetary mission spacecraft was used for this kind of comet observation, and it worked beautifully. The data from JYC helped refine the trajectory calculations for 3i Atlas with greater precision than would have been possible using Earth-based observations alone. And here's the exciting part: this technique can be used for future interstellar visitors too. We now have a proven method for getting extremely accurate position and trajectory data using spacecraft that are already out there for other purposes. The JUIC observations also do something else important. They demonstrate that when the spacecraft reaches Jupiter and begins its primary mission, the science team will have experience using these techniques, and future comets or interstellar visitors that happen to pass through the solar system while JUIC is operational could be studied with similar methods. We're building an institutional knowledge base, accumulating expertise in how to observe these rare events. Ground-based telescopes around the world are also focused on 3i Atlas during December. Professional observatories in both hemispheres have scheduled observing time to track the comet, gathering data that complements what space telescopes can see. Ground-based observations have the advantage of being able to dedicate extended time to monitoring how the comet changes night by night, tracking variations in brightness, watching for outburst events where activity suddenly increases, and measuring the precise details of how the tail and coma evolve. Some of these observations are using specialized instruments designed to detect polarization in light reflected from the comet. Polarization measurements can reveal information about the size and properties of dust particles being released by the comet, which in turn tells us about the physical characteristics of the surface material. Other observations are focused on tracking the comet's rotation, trying to determine how fast it spins and whether that rotation is simple or complex. All of this data serves multiple purposes. On the immediate level, it helps resolve the specific mysteries about 3i Atlas, the unusual jet behavior, the brightness variations, the composition questions. But on a broader level, every piece of data contributes to our general understanding of interstellar objects. With only 3 confirmed interstellar visitors, we're still in the very early stages of understanding what's normal for these objects and what constitutes a genuine anomaly. Each new observation expands our catalogue of knowledge. The timeline for results is important to understand. Some observations produce immediate data. Images can be processed relatively quickly, and basic measurements can be extracted within days or weeks of observation. But the more detailed analysis, particularly composition studies and trajectory refinements, takes longer. The data has to be carefully calibrated, compared against models, and verified through multiple analysis techniques before results are published in peer-reviewed journals. The JUIC parallax observations, for example, provided data that was announced recently, but it took time for scientists to process those measurements and confirm the results. We can expect a similar timeline for December observations. Images and basic findings will likely become available within weeks. More detailed compositional analysis and interpretation will take months. By late winter, we'll probably have a much clearer picture of what 3i Atlas is really made of, and whether its unusual characteristics can be fully explained by natural processes we already understand, or whether they represent something genuinely novel that requires expanding our models. There's also another observation opportunity coming later. When 3i Atlas passes through Jupiter's region of space in the spring, there will be another chance to observe it, though by then it will be farther from the Sun and likely less active. That later observation could still be valuable for confirming findings from December, and for tracking how the comet's behaviour changes as it moves through different regions of the solar system. What could these observations potentially reveal? Several scenarios are possible. The most likely outcome is that the data will explain the unusual characteristics we've been discussing through natural mechanisms, perhaps an irregular rotation state, or a heterogeneous surface composition, or structural features that cause jets to be directed in particular ways. This would confirm that 3i Atlas, while interesting, is essentially a natural comet following understood physics. Another possibility is that the observations reveal something genuinely unexpected that doesn't fit current comet models, some composition or behavior that requires scientists to expand their understanding of what comets can be. This would be scientifically valuable, because it would mean we're learning something new about the diversity of objects in the galaxy. The least likely but most sensational outcome would be finding evidence that genuinely challenges natural explanations and lends support to more exotic hypotheses, like Loeb's artificial influence ideas. This would require discovering characteristics that have no plausible natural explanation despite serious effort to find one. Most scientists consider this outcome extremely unlikely, but the point of doing observations is to test hypotheses, including unlikely ones. Whatever the results turn out to be, the December observation campaign represents modern astronomy at its best. Coordinated international effort, multiple complementary observation techniques, careful data analysis, and open sharing of results for scientific debate. This is how we advance our understanding of the universe. Not through speculation or assumption, but through observation, measurement, and rigorous analysis. And regardless of what we learn about 3i Atlas specifically, the observation campaign itself is advancing our capabilities for studying future interstellar visitors, building expertise and techniques that will be available when the next mysterious object appears. Because there will be a next one. Our detection capabilities are improving, our telescopes are becoming more sensitive, and our survey coverage of the sky is expanding. We'll find more interstellar visitors in the years and decades ahead, and each one will teach us something, adding to our understanding of what exists in the galaxy beyond our small corner of space. That's the larger context that makes these observations matter. We're not just studying one comet, we're building humanity's knowledge of the interstellar environment, one visitor at a time. Step back from the specific details of 3i Atlas for a moment and consider what's actually happening here at a higher level. For the first time in human history, we're living in an era where we can detect, track, and study objects that come from beyond our solar system. That's a profound change in our relationship with the cosmos, and it's worth reflecting on what that means for humanity's future. Every previous generation of humans lived under the same stars, but was completely blind to events like this. Interstellar objects passed through our solar system countless times throughout history, during the age of dinosaurs, during the rise and fall of ancient civilizations, during the world wars and space race of the 20th century. They came and went without anyone noticing, invisible travelers moving through the darkness while humanity remained unaware. We couldn't see them, couldn't track them, couldn't learn from them. That's changed now. We've built the telescopes, developed the mathematical tools, created the observational networks, and trained the scientists to detect these visitors. We've given ourselves eyes on the cosmos in a way no previous generation possessed. And with that capability comes knowledge, opportunity, and responsibility. Each interstellar visitor we detect adds crucial data to our understanding of what exists beyond our solar system. With only 3 confirmed detections so far, we're still in the earliest stages of building a catalogue of interstellar object types. We don't yet know what the full range of diversity looks like. Are most interstellar visitors relatively similar, or is each one unique? How common are comets versus asteroids in interstellar space? What does the composition of these objects tell us about star formation and planetary system evolution in different parts of the galaxy? Oumuamua taught us that interstellar objects can have truly bizarre characteristics that challenge our initial assumptions. Its elongated shape and unusual acceleration created debates that still haven't been fully resolved. Borisov taught us that some interstellar visitors closely resemble objects from our own solar system, suggesting that comet formation processes might be similar across different stellar environments. Now 3i Atlas is teaching us about the edge cases, the objects that don't fit neatly into simple categories, and how to distinguish genuine anomalies from natural variation. This knowledge accumulation serves a practical purpose beyond satisfying scientific curiosity. As we discussed earlier, cosmic impacts are real threats, rare but devastating. Building a comprehensive understanding of what travels through interstellar space, how these objects behave, and how to detect them is part of planetary defense. We need to know not just about the asteroids and comets native to our solar system, but also about the possibility of fast, moving interstellar impactors that could arrive with less warning time than solar system objects. The fact that we successfully tracked 3i Atlas, calculated its trajectory with precision, and confirmed it poses no threat demonstrates that our planetary defense systems work. We can see these objects coming. We can assess the danger level accurately. That capability didn't exist a generation ago, and it's improving with each new detection and each new observation campaign. Every interstellar visitor we successfully track is a validation of our detection networks and an opportunity to refine our techniques. There's also the question of learning to distinguish natural from artificial, which is part of what makes A.V. Loeb's approach controversial, but also potentially valuable. In a galaxy with billions of Earth-like planets, where the ingredients for life appear to be common, the possibility that we might someday detect an artificial object passing through our solar system isn't pure science fiction. It's statistically unlikely in any given decade or century, but over long timescales, if technological civilizations exist elsewhere, and if any of them send probes into interstellar space, eventually one might pass through our cosmic neighborhood. Being able to recognize such an object, if it ever appeared, requires having baseline data on natural objects, knowing what comets and asteroids from interstellar space typically look like, so that something genuinely anomalous would stand out. That's part of what we're building now. Whether you agree with Loeb's specific claims or not, the general principle is sound. You can't identify the unusual unless you thoroughly understand the usual. Beyond the practical aspects, there's something philosophically significant about humanity becoming observant of its cosmic environment. For most of our existence, we were trapped in a kind of cosmic provincialism, aware only of our immediate surroundings, blind to the larger structures and processes at play in the solar system and galaxy. We're now transitioning into a state of cosmic awareness, building knowledge of our neighborhood, understanding the dynamics that govern motion on solar system scales, recognizing that we exist in a larger environment with ongoing processes that occasionally touch our world. This awareness changes how we think about our place in the universe. We're not isolated. We're not in a static environment. We're part of a dynamic system where things move, where objects from distant origins pass through, where events on cosmic scales create risks and opportunities that affect life on Earth. Understanding that context, building that awareness, is part of maturing as a technological civilization. The capabilities we're developing now, the detection networks, the analytical techniques, the coordination between observatories and space agencies, these are infrastructure investments that will serve humanity for generations. Every improvement in our ability to detect and characterize these objects makes us safer and more knowledgeable. Every scientist trained in these techniques, every software system developed for trajectory calculation, every successful observation campaign builds institutional knowledge that persists and grows. We're also living in a remarkable moment historically. We're the first generation able to do this. Future generations will look back at this era as the time when humanity first opened its eyes to interstellar visitors, when we transitioned from cosmic blindness to cosmic awareness. In 1,000 years, historians of science will mark this period as significant, noting the first detections of interstellar objects and the early efforts to understand what they revealed about the galaxy. And there's an element of shared human experience here that's worth appreciating. Regardless of nationality, politics, religion, or any other division that separates people, we all share the same sky. When 3i Atlas passes by in December, it's passing by everyone. The discoveries made about this object belong to humanity collectively. The knowledge gained becomes part of our species' understanding of the cosmos. The safety confirmation protects everyone on the planet equally. In a world that often feels fragmented, where people are divided into groups that struggle to understand each other, astronomy offers moments of unity. We're all inhabitants of the same planet, looking up at the same universe, asking the same fundamental questions about what's out there and what it means for us. Objects like 3i Atlas remind us of that shared context, that cosmic perspective where our differences shrink and our common situation becomes clearer. The investment in astronomy, in space observation, in building the tools to study objects like 3i Atlas isn't just about abstract knowledge. It's about ensuring humanity's long-term survival by becoming aware of and able to respond to cosmic threats. It's about expanding our understanding of the universe we inhabit. It's about building the knowledge base that future generations will use as they reach further into space. It's about fulfilling the deep human drive to explore, understand, and make sense of our environment. Every time we successfully detect and study an interstellar visitor, we're proving that we can do this. We're demonstrating that human intelligence, cooperation, and technology are sufficient to observe and understand cosmic phenomena. We're building confidence in our capabilities and identifying areas where we need to improve. That process of discovery, learning, and improvement is how civilizations advance and how humanity ensures its future in a cosmos that's vast, ancient, and full of processes we're only beginning to comprehend. So let's bring this all together and answer the question one final time with complete clarity. Is 3i Atlas heading our way, and are we in danger? It is heading through our solar system, passing relatively close to Earth in astronomical terms. But no, we are absolutely not in danger. The object poses zero threat. That's confirmed by multiple space agencies, using precise observations and mathematical modeling that leaves no room for uncertainty about the trajectory. You can watch this cosmic event with curiosity and wonder rather than fear. What have we learned by investigating this together? We've learned that 3i Atlas is the third confirmed interstellar visitor ever detected by humanity, a comet from beyond our solar system that's providing scientists with valuable data about what exists in the space between stars. We've learned that it has some unusual characteristics: trajectory alignment with our planetary plane, jet behavior that doesn't perfectly match simple models, brightness variations that suggest complex surface properties or rotation. These characteristics have sparked scientific debate, with some researchers like Harvard's A.V. Loeb suggesting the statistical probability of the trajectory being purely natural is very low, while most astronomers argue that natural explanations remain sufficient. We've learned that unusual doesn't mean dangerous. The controversies about 3i Atlas's characteristics are entirely separate from questions about safety. An object can be scientifically puzzling and still pose no threat whatsoever. We've also learned about the broader context of why these objects matter. They're teaching us about cosmic diversity, building our catalogue of interstellar object types, improving our planetary defense capabilities, and expanding humanity's awareness of its cosmic environment. The December observations happening right now are gathering data that will help resolve some of these mysteries. Hubble Space Telescope, ground-based observatories, and spacecraft like JUIC are all contributing pieces of the puzzle. Within weeks, we'll have initial findings. Within months, we'll have detailed compositional analysis and better understanding of whether 3i Atlas's unusual features can be fully explained by natural processes, or whether they represent something genuinely novel that requires expanding our models. Here's what remains genuinely mysterious and worth following. The composition analysis will tell us what this comet is made of and how that compares to both solar system comets and to Borisov, the other well-studied interstellar comet. That comparison could reveal patterns about how star systems form and evolve. The jet behavior analysis will help determine whether the directional preferences some observers have noted are real anomalies or artifacts of the comet's rotation and surface properties. The brightness variation studies will tell us about the object's shape, rotation state, and surface heterogeneity. There's also the continued question of whether the trajectory alignment is truly as statistically improbable as Loeb suggests, or whether there are natural selection effects or galactic dynamics that make such alignments less surprising than pure random chance would indicate. That's a question that will be resolved not just by studying 3i Atlas, but by accumulating data from future interstellar visitors and building statistical understanding of the population as a whole. What matters as you continue to follow this story is learning to distinguish between confirmed science and speculative interpretation. Confirmed 3i Atlas is an interstellar comet. It's safe, it has some unusual characteristics. Speculative interpretations of what those characteristics mean, whether they suggest anything beyond natural comet behavior, whether they indicate artificial influence. The distinction between observation and interpretation is crucial for understanding science as it's actually practiced. Data is collected, multiple interpretations are proposed, evidence is gathered to test those interpretations, and over time consensus emerges around the explanations that best fit all the available evidence. This process takes time. It requires patience to let scientists do their work, rather than demanding immediate definitive answers. But that patience is rewarded with reliable knowledge rather than premature conclusions. The December observations of 3i Atlas will provide data that takes months to fully analyze, but when the results are published in peer-reviewed journals, you'll know they represent careful, rigorous science rather than speculation. As for when we'll get those results, initial observations and images are already being released and will continue throughout December as the comet remains bright enough for detailed study. Preliminary findings from Hubble and ground-based observatories will likely be announced within weeks after observations are complete. The JUIC team has indicated that detailed analysis of their parallax observations will be published in late February. More comprehensive studies analyzing all the December data collectively will probably appear in scientific journals throughout the spring and into next year. This is the normal pace of astronomy. Observation happens relatively quickly, but analysis and publication take time to do properly. And then 3i Atlas will continue its journey back into interstellar space, leaving our solar system behind forever. It will travel through the darkness between stars, perhaps for millions of years, until it eventually enters some other stellar system where, if any astronomers exist there, they'll detect it as their own interstellar visitor, asking the same questions we've been asking, learning what they can during the brief window when it passes through their cosmic neighborhood. Meanwhile, we'll continue building our detection capabilities, improving our telescopes and survey systems so that the next interstellar visitor is detected even earlier and studied even more thoroughly. We'll continue cataloging near-Earth objects to ensure we know about any potential impact threats with enough advance warning to do something about them. We'll continue asking questions about the universe, building knowledge one observation at a time, expanding humanity's understanding of the cosmos we inhabit. For you, the person who watched this video because you wanted to know whether we're in danger from 3i Atlas, I hope you've gotten more than just a simple yes or no answer. I hope you've gained some understanding of how scientists assess these questions, why the unusual characteristics of this object matter, even though it's not dangerous, and what it means that we're living in the first era where humanity can detect and study visitors from beyond our solar system. Stay curious. Keep asking questions. When headlines about cosmic events sound alarming, look for the actual science beneath them. Understand that unusual doesn't mean threatening, that scientific debate is healthy rather than alarming, and that the fact we can have these discussions at all represents remarkable progress in humanity's relationship with the cosmos. New data from December observations will arrive in the coming weeks and months. If you want to stay ahead of the headlines and get the real science as it happens, without the sensationalism, and with the context you need to understand what it means, subscribe and hit notifications. And tell me in the comments, what aspect of 3i Atlas fascinates you most? The mystery of its unusual trajectory, the opportunity to study material from another star system, the demonstration of our planetary defense capabilities, or something else entirely? Let me know where you're watching from, And what made you click on this video? Were you genuinely concerned or just curious? Let's keep investigating these cosmic mysteries together, because this is just the beginning of humanity's journey into understanding the interstellar visitors that pass through our neighborhood. 3i Atlas is heading our way, and no, we're not in danger. But yes, we're absolutely witnessing something extraordinary. A visitor from the stars, a messenger from the galaxy, a reminder that we're part of something vast and ancient and ongoing. And we have the privilege of living in the generation that learned to see these visitors and understand what they mean. That's not something to fear, that's something to celebrate and appreciate and learn from. The cosmos is speaking. We're finally able to listen. And what we're learning is just the beginning of a much longer story about humanity's place in the universe.